3.3 with Algebra 2, Semester 2, on applications of exponential functions. So for this assignment or lesson, there are going to be some story problems that we're going to just see how exponential functions are used to solve different kinds of problems. So first of all, we have a chessboard, and the inventor of the game of chess is said to have asked for the following reward for his invention: 1 grain of rice on the first square, 2 grains on the second square, 4 grains on the third square, 8 grains on the fourth square, and so on. So how would you represent this situation using an exponential function? Well, we know that on the first square has 1, and then he's doubling the number of grains on each additional square. Other piece of information that we need to know is how many squares are on a chessboard. Chessboard has 8 by 8, so 64 squares on a chessboard. Okay, on the first square, we are going to have 0. We're going to call that square 0 because it works with the math better, but we can do it either way. Anyway, we have 1 grain of rice. Then 1, this is like times 0, okay? So at times 0, I have 1 grain of rice, box 0, whatever. Then I move to the next one. I'm going to double it and double it and double it and double it. So can we write this as a mathematical equation? Well, we're doubling, so that's a power of 2. 2 to the what power? Well, 2 to the first power is 2, 2 to the second power is 4, 2 to the third power is 8, 2 to the fourth power, and 2 to the 0 power is 1. So the reason that we kind of wanted to start at 0 is because 2 to the 0 power is 1, and if I had started at 1, then I should have started with 2 grains of rice, and that didn't make sense for the problem. So basically, square 1 is actually times 0, or starting at 0. So I'm going to do this up to 63 squares. So what is the equation that I'm using? I'm just using 2 to the x power. And so to figure out this one, I would do 2 to the 63rd power, which is huge. So if you want to see that answer, I'm going to let you put that in your calculator because it's going to be in scientific notation for you. So what was my equation? It's just y equals 2 to the x. And when is this valid? Well, for this problem, obviously, I'm not going to have a negative square, so we're not going to have negative numbers, and I want to stop at 63. So the domain for this problem is 0 less than or equal to x less than or equal to 63, and it's actually just the integers in between 0 and 63 that we're plugging in. If I was just looking at this as a math equation, the values of x could be any real number. So I could plug in negatives, I could plug in positives, I could plug in decimals, and I could get an answer. But for the context of this problem, I needed to keep it from 0 to 63 and whole numbers. I think that concludes this problem. Let's go on to the next one. So that was kind of individual sets of points. This one is something that grows kind of a little more continuously, like this is pollution or population or exponential decay of radioactive material, growing bacteria. All those kinds of examples that happen naturally are going to use the PERT equation that we talked about in the last lesson, with it basically compounding continuously or growing continuously. So I'm just going to write that down because we're going to use that formula. So this one says in 1970, so that's kind of our starting time, the amount of industrial pollution in Brady Lake was 3 tons. That would be my starting amount. Since then, the amount has been doubling every 8 years, giving a growth rate of, so this is my rate. They tell me it's doubling every 8 years. That's actually not numbers that we're going to use in the equation because we already have it. We already were given the rate. They basically used those to figure out this decimal here. If the pollution is not controlled, when will it reach 50 tons? So let's start with writing our equation. A equals, P is the starting amount, which was 3, times e to the, they gave me the rate, but I need to write it as a decimal, so move over 2 decimal places, 0.0866. T, I'm going to use T because T is time. You can use X, it doesn't matter. You can use y equals and with an x, or you can use a equals with b. It doesn't really matter too much on the which variable you use. Now, in the context of this problem, what can my t be? So what is my domain for t? Well, my information started in 1970. That is at time 0, and it just goes on. So this could go forever. I'm not sure, but we can go greater than or equal to 0. If it was math equation and we didn't have a context, it would be all real numbers. Okay, now the question asks, when will this equation reach 50 tons? So I actually want to know when the 50 will equal the equation. And they were really nice and graphed it over here for me. So here's the graph of the equation. On Apex, they'll either give you the graph, they'll give you the equation, and then ask you. And so if they give you the equation, or if they give you the graph, I want to know when this equals 50. Well, here's 50. So when is that? So I'm going to go down here. Try to keep it straight. That was pretty good. So somewhere in this box, which these are by 2, 4, 6, 8, 10. So somewhere between 32 and 34. Actually, it's a little lower than that if you look at that. So between 32 and 33. 32 and 33 what? Well, years, because we found time. Down here, this is time, and this is years. So 32 and 33 years after 1970, because 1970 is when it started. So basically, the years 2002 and 2003 is when that was. So this answer is acceptable between 32 and 33. But just to be clear, it's 2000. You would add that to 1970. So this problem we can also solve on the calculator. So to do that, I'm going to show you how, because you probably haven't done very much of this on the calculator before. So first, we need to get this equation in the calculator. So you press y equals, and in y1, you're going to put the equation that we have here. In y2, you're going to be putting what we want it to equal, which is 50. So I showed that on my calculator. So you push y equals, and then put those data in. Now, I want to see it on my graph before we try to solve this. So to see the graph, if you push graph right now, you're going to get a 10 by 10 window, and you're not going to see where we want to see. So we have to change the window. We want to see from 0 to 50 is big enough. So you change, you press the window button, which is right here, and then you change your X-min and X-max from 0 to 50. The scale is just how often you want tick marks, so it doesn't really matter if you change those on your calculator or not. And then Y-min and Y-max, I want to see this here, so I'm going to go from 0. I want to go past 50, so let's go all the way up to 70. And then now you can press the graph button. So change your window and then press graph. Your graph should look like the picture down here at the bottom of the screen. And the last thing is, I want to know where that point is. So this is the part that's probably new. To find this point of intersection, you press second trace. And I will often say press second calc, because if you look in the tiny little words up above there, it says calculate or calc. So you press second calculate, and then I think usually it's number 5. Number 5 says intersect. We're looking for the intersection, so you press number 5. And then this is the part you gotta figure out. You start out with a little flashing cursor somewhere on your screen. The deal is we have to tell our calculator where we are looking for an intersect, and our calculator only knows left and right. Okay, so don't push any buttons except left and right. If your cursor's down over here, you might want to move a little closer, so it should be like about here. Somewhere to the left of this point. You can be closer if you want to be, it doesn't matter. Then you press enter once. When you press enter, it should hop up to the other function. If it doesn't, then you didn't do something right. So let me go back to the beginning. You push second calc, push number 5, and then somewhere to the left of your intersection, you press enter. When it hops up here, then you're going to arrow to the right until it's over here somewhere. So you're basically going to be somewhere where the intersection is between your first enter and your second. When you press enter over here, the bottom of your screen is going to say, guess. Well, you don't have to guess. You can just press enter again. So really, this is what I say. Press enter on the left, go to the right, press enter twice. Enter, enter. You just can't be too fast about it or your calculator will get grumpy. All right, after that, what happens is it should have a flashing little box on the intersection, and down at the bottom, it will tell you, hopefully I can make this bigger and show you. Oh, my computer is thinking, so just a moment. There we go. That it will tell you the actual value of the intersection. So the answer is 32.487. That's when it equals 50. And our answer before from just guessing was between 32 and 33. It's actually 32.487. So you can just be a little more precise. Anyway, so to review, find an intersection, you press second calc, go to the left, hit enter once, go to the right, hit enter twice. That's the new skill that I want you to have with your calculator today. So let's try it one more time to make sure you've got that down. So here's another example. We've got an exponential function. They don't give you the function on this one, but if you were on Apex, they would give it to you. So I'm just going to give you what it is. It starts at 100. It's actually like 100%, and then it's decreasing. So this over here is in percent. So my numbers are between 0 and 100. Times e to the, this one's actually decay. Notice it's going downhill. So they gave me a decay rate. I need to make it negative in my function. And I need to move the decimal over twice. So if I move it over twice, I'm going to have 0.000121 t. So e is to the negative because it's decay, 0.000121. All right, we've got our equation, y equals. The domain of this is time is greater than 0 again. And when will it reach 2.1%? So we're going to do this in the calculator again. In y1, put your exponential function. In y2, put 2.1. It is a percent, but that's actually my output is in percent, so don't move the decimal. And we're going to graph that. So when you graph this one, the time ends up being huge. And the only reason you can tell kind of what it's going to be is because of this graph right here. So if you didn't have this graph, you'd have to experiment with your calculator. But I'm going to tell you that if you want to see this and the line 2.1 on your computer very well, you're going to need to change your window because 10 by 10 is an awfully little section of this. So make sure you change your window. I put some window settings down here that can help zoom in on that quite a bit. So if you change your window to between 30,000 and 35,000 and from 0 to 5, you're basically going to zoom in on this point of intersection right here. Once you do that, you should get a graph where there's a slightly decreasing. That would be the exponential one, and a line, and you want to find that point of intersection again. So remember the buttons. Second, calculate. Number 5, the intersect. You want to be on the left when you start out because this is y1 is probably your cursor's up here. Press enter, go to the right, make sure you're on the second graph. To switch between graphs, you hit up and down, but you shouldn't need to do that because when you hit enter, it jumps to the other graph. Then you press enter twice, and it should zero in on the center point here, which is 31927. I'm actually doing that from memories from my class, so I think that's it, but I know it's 319. So that's your X. So that's the number of years right here when it gets down to 2.1%. Okay, for this last problem, we're going to look at some things that grow exponentially and then they kind of top off. So example, if you're growing bacteria in a petri dish, it grows faster and faster and faster exponentially, and then eventually we kind of reach a maximum population that can live in the Petri dish. So some of them start dying off because it can't just keep growing forever. So this exponential looking graph that then tops off and has an upper limit is called logistic. So it's said to have logistic growth. Okay, with logistic growth, the early stages of growth are nearly exponential. And then as it gets closer to the maximum, it actually slows down. So if we were looking at the rate, it's going faster and faster and faster and faster and faster, and then it's slowing down and slowing down and slowing down to almost nothing again. So both of these blanks up here are just logistic growth. Okay, so just so you can see an example of what this looks like and get it in your calculator, this is the recycling problem. So in 1960, less than 1% of families in Newton, some town, recycled. A new project was started to encourage more recycling. Since then, the percentage of recycling families has been growing according to a logistic growth equation over here on the right. So because this is percent of people recycling, at the beginning, they're probably going to get a lot more people to recycle, and they can never go over 100%. So kind of my maximum that it can ever get up to is close to, but probably never equal to 100% people are recycling. All right, so I just wanted you to see what this looks like in your calculator. So in your y equals screen, press y equals, and you're going to type this in. Make sure that you put parentheses around your entire denominator, and after the e, you probably need another set there. So when you type it in, it's 100 divided by parentheses. 1 plus 400 times e to the negative 0.15 x, because your calculator doesn't really have a t. We're just going to use x anytime it has a variable in the calculator. Okay, I want to see this. So to graph it, I'm just going to give you the window, put from 0 to 100 and 0 to 100. I know that the y max is going to be 100 because of this 100 up here, and the x is time, so I don't know how long it will take, but I've already done this in my calculator so that I could take a look at that and see what it looks like. So we'll solve those in a second. So on your calculator, it should look something like this. From 0 to 100, 0 to 100, you get a really nice logistic curve there. So that is what I want you to be able to do, but there's also solving it. So what would be the percent in 1980? Well, this started in 1960, so that would be t equals 0. So in 1980, that's t equals 20. So all you need to do is put a 20 in here. So you can do it on the graph, or you can just type it in on your normal calculator screen. If you want me to show you how to do it in the graph, all you do is press second, calculate, and this one's number 1, the value. And then at the bottom of the screen, it's going to say x equals, and you just put in a 20. And then it will tell you the y value, and you write it right here. And for the next one, you're just going to do the same thing again. Second, calculate the value at x equals, how many years is 2040 after 1960? 80. So you put in an 80, and your y equals value would be the answer. So that is the end of lesson 3.3. Your checkup only has 6 problems, and there are no quizzes for this lesson. So please do those 6 problems, and that will be it.